Now let's look at the third step in efficient binocular signal coding. This step is multiplexing. It is after the decorrelation step K0, transforming left and right eye input to ocular summation and ocular difference. And the next step, gain control, transforming summation and difference into O plus and O minus, the gain controlled version. Then the third step is U. It is another rotation, rotating this two-dimensional vector, O plus and O minus, or two-dimensional coordinate system, O plus and minus, to final output, O1 and O2. So you're putting this rotation matrix, acting onto it, this is the result. Here's an example when you have O plus and O minus axes. You rotate by 45 degrees clockwise, you have O1 and O2. And this is actually a special example when the rotation is the opposite of the original rotation K0, such that you go back to the original axis direction for the left and right eye input. In principle, you could apply other rotation theta, angle theta for the U matrix. And so therefore, in general, you actually just have O1 as a particular mixture of O plus and O minus, and O2 as another particular mixture of O plus and O minus. So that's multiplexing. And combining this together, so AK, the efficient coding transform, really is combining three matrices. K0, decorrelation, G, gain control, and U, multiplexing, transforming the original signal left and right eye input to the final inputs to the two neurons, O1 and O2, the two final encoding neurons. And plugging these matrices in, you're putting that, and this you can work it out to verify that this is indeed the case. Let's work out the O1 and O2 in an example when the rotation angle is this special case of minus 45 degrees. You plug in these sine and cosine value for this angle, you get this result for O1 and that result for O2. And since S plus is the summation of the left and right eye input and S minus is the difference, you plug it in and you find that this is the outcome. And similarly for O2, you get this outcome. And this is the contribution of the left eye input to O1. And so therefore you can see that the sensitivity to the left eye input is the difference between these two gains. And this is the contribution from the right eye input. The sensitivity to the right eye input is the summation of these two gains, G plus and G minus. So obviously this neuron's gain, the sensitivity, is stronger to the right eye input. So this is a right eye dominant cell. And analogously, you'll find that this second neuron for O2 is a left eye dominant cell. And if you write each of the O1 or O2 as a linear weighted sum of the left and right eye input, then these two weights corresponds to these two sensitivities. And you can, from these weights, calculate the ocular dominance indices that correspond to the experimental measured data to compare the theoretical predictions with experimental data. Coordinate rotation should not change the length of a vector, so the summation of output squared stay the same before and after the rotation. So before the rotation is O plus square plus O minus square, and after is this. And therefore the total output power is unchanged by this multiplexing. Now let's calculate the correlation between the output O1 and O2. So O1 is these values, plug it in, O1 here and O2 there. And then expand the terms out, we collect them together, it becomes these two terms, okay? and you look at the second term is proportional to the correlation between O plus and O minus, and these two are not correlated, so the second term is 0, and so therefore we just have the first term left. That's the correlation. Let's look at this correlation when the signal to noise is very large. In such a case, we have contrast enhancement with a larger gain, G minus, for the weaker binocular difference channel, which has a smaller signal power. And this larger gain is so much that you achieve whitening such that the output power is equal between the O plus and O minus channels. So you plug this into that, then you achieve O1 and O2 are decorrelated. And this decorrelation, you can see obviously already from this graph because of this spherical distribution, O1 value and O2 value are really independent from each other. And this is so not just for the special O1 and O2 direction with minus 45 degree rotation by this U matrix. You can even rotate in any other angle, they are still decorrelated because this is spherical, so projection of data onto any two orthogonal axes will be decorrelated. Now let's look at the case when the noise is very large. Recall that in this situation, the distribution of signal plus noise is a near spherical distribution with a slightly larger variance along the binocular summation direction. And the gain control will downplay or abandon the binocular difference channel signal so that the final distribution is much more ellipsoidal and with emphasizing signal along this direction by a gain bigger in that summation direction. And so that the variance is obviously going to be much larger in the summation channel than the difference channel. And with such unequal variance, and from this we know the two outputs O1 and O2 should be correlated. And this correlation is obvious from this graph. You can see they are correlated even if you have some other angles of rotation in this U matrix when the theta is not that special, minus 45 degrees. And of course, you can also have a very, very special rotation such that there's no rotation at all. You just go back to the O plus O minus direction. In such a case, theta equal to 0, you will also have decorrelation. But otherwise, in general, O1 and O2 are correlated with each other. And such correlation creates redundancy. And so output is now redundant in the O1 and O2, and such redundancy should help with error correction in this noisy situation. So therefore we see that this efficient coding can create decorrelated outputs when signal noise is high enough in the noise-free situation especially, and you should create correlated or redundant responses when the noise is too high. Whether you have a high signal-to-noise ratio or low signal-to-noise ratio, given any signal-to-noise ratio, you will have many possible transformation K, okay? Simply because you have many possible transformation U, so many possible choices of theta. And so there is a group of most efficient coding solutions in our definition of the objective function EK. However, among these, there is one U multiplexing that's special. That's when the U is the inverse of K naught. So in our case, when the theta is minus 45 degrees, that will make U the opposite rotation of K naught. In general, this will give the least distortion between the O's, output O1 and O2 in this case, and S, the input SL and SR in this case. So it's the least distortion in the transformation encoding transform. And this is mathematically, you can prove it that way, but intuitively you can see in a special case when you have this G matrix equal to 1 identity, okay? Then you can remove this G, and then when U is the inverse of K naught, then the K will be basically identity matrix. That means you go from S directed to O without any mixing or gain control. So the left eye input go to O1, the right eye input go to O2. Okay, and this will save you a lot of neural wiring, and that's indeed the case. It will save you a lot of neural wiring when you have minimum distortions. And we will, so the saving this minimum wiring, of course, is not in the objective EK, but sometimes it could be useful there as additional neural cost if you like to include it. And we will often use this U, and we will see later in examples of spatial coding, for example, how it can lead to very localized recidiv fields.